Let's start. Today, I will start by a residual topic from yesterday. As you may remember, we were just briefly introducing some of the topics about signals that we will cover throughout this semester. And we started by even and odd signals, and then we talked about periodic signals in discrete time, or we also started with discrete time and continuous time signals and said that they are different. I didn't show you how to notate them though. I will do that quite soon. And finally we have seen the unit step function, if you remember. Now the signal that is left from yesterday is a single one, which is quite important. It happens to be quite important for this course, and that is called the unit impulse. We will come back to the utilization or more rigorous definitions of this unit impulse thing. In continuous time, it's quite a problematic function, problematic signal, because it actually corresponds to the time derivative of u of t, and it is notated by delta t. Okay. As you see, u of t was discontinuous, so a discontinuous function is not differentiable. So what does its differential correspond to? Well, it's a definition. It really doesn't correspond to anything physical, but it will help us solve a lot of problems. We will notate our signals in terms of this unit impulse, which doesn't physically exist. So it's a hypothetical signal, and it's a limiting signal under some certain circumstances. And what is that? This delta of t, by the way, since the derivative of unit step is the impulse, then the time integral of the unit impulse would correspond to u of t from the fundamental theorem of calculus. What I have just written is the fundamental theorem of calculus, if you remember. If there is an integral, then the opposite is the derivative, or vice versa. One thing that I found the students a little bit careless is about this integral definition. As you see, the integration starts from minus infinity and it goes up to t. It's a time, and the time appears on the integration upper limit. It's not in the evaluation of the integral. It's not delta t dt. If you write delta t dt, then is it the variable of integration or is it the limit of the integral? It will be confused. So that's why I use a different notation. By the way, this happens to be the Greek letter tau, which is analogous to t, but in order not to confuse t with t, I use tau. You could use lambda, for example. That's what you can do. So it's such a function that if you integrate from minus infinity up to a certain time interval, let's see what happens. This is your time axis. Suppose that your 0 is somewhere here. Okay? And let's assume that your first t corresponds to somewhere here. It's not f, of course, it's t. And this is the tau axis. So we integrate along tau from where to where? From minus infinity up to this time. And when I integrate it, if t is less than 0, what happens? It will produce u of t value for t is less than 0. What was the unit step function value for t is less than 0? Do you remember this unit step function? So what is the value before 0? Before t is equal to 0? 0. So all the integrals, all the integrations must give you a 0. Which means that delta t is also 0 all over those left-hand side portions. From minus infinity up to 0, everything is 0. What about another choice of t? Let's choose this time t here. And let's integrate from minus infinity up to this time instant. Then it would produce u of t for a t value greater than 0. And what is that? It is 1. So something happens in between. The integral jumps to 1 and it goes on like that. If it goes on like that, it means that the value of the impulse function, unit impulse function, delta t function, is also 0 after 0, because it doesn't change. It doesn't accumulate anything further. So there is nothing. And you can see from the derivative of the unit step, it's all zeros for the negative value of t. It's all zeros for the positive values of t. It is only non-zero at t is equal to 0. Something happens only at t is equal to 0. So it is all zeros here. And it is all zeros here too. What is it in between? The notation, the way to plot this unit impulse response is like this. It's an arrow going upwards. Okay, that's how we notate it. And we indicate its magnitude, but its magnitude is not its height. Okay, it's not like the magnitude of a continuous function. It is something else. But this, as I say, is a unit impulse, so its magnitude is unity, 1. So we notate it like this. We put a 1. We put an arrow and write 1 on it. And the position that we put that 1 impulse is the position of the impulse. That is delta t. Let me ask you a quick question. Can you plot, this time it will be on the t-axis, can you plot delta t minus 1? It's again, or let me ask it like this. Example is 2 delta t minus 1. Where will you plot it? This is your axis. This is 0. So the arrow is at 1. Right? It must be here because it's shifted towards right. And we put an arrow, preferably a twice longer arrow, and then put a 2 and indicate its position. So its magnitude is 2. What does this magnitude correspond to? It corresponds to this. It's the area under the impulse. So the area under it must be evaluated from minus infinity to infinity by an integration. Delta t dt. This thing is equal to 1. This is the magnitude. It's not the height, but it's the area under that function. Let's start with another signal, and let's see how we can achieve a unit impulse from that. And that is a box signal, d of t. This is not a very commonly used signal. It's a rectangular signal. Sometimes they also denote it by rect of t in books. It is something like this. It is a box-shaped signal from minus 1 over 2 to 1 over 2 with height being 1. This dt has one common property with delta t. It shares one property. The area under it is also equal to 1. Okay? What's the area here? It's equal to 1. So integral from minus infinity to infinity d of t dt is equal to 1. Now you can think of, or you can imagine what kind of a signal delta of t from here like this. Let's make this dt narrower meanwhile increasing its height. For example, let's make it start from minus 1 over 4 and go up to 1 over 4. But this time its height would be equal to 2. What is the area under it? Again 1. It's the same. The area didn't change. I just made it narrower and taller so that the area doesn't change. This new signal is d of, in terms of d of t, can you indicate what this signal is? It's not d of, it is 2 times d of what? T over 2. If it is t over 2, then at 2 it will be dt, so it's 2t. Okay. I can change it like this as well, right? From 1 over 8, from minus 1 over 8 to plus 1 over 8, and make it like this. And it will be a different thing. It will be 4d for t, like this. So as you see, I can make it arbitrarily narrow and arbitrarily tall. And in the limiting case, as I increase these scales to infinity, or in more mathematical terms, let me write it like this. I will make a limit as epsilon goes to 0, 1 over epsilon d t over epsilon. This time I am decreasing epsilon, or you can say 1 over epsilon is alpha, and say this is also equivalent to limit as alpha goes to infinity, alpha d alpha t. These two are the same things. And those limits are both equal to delta of t, as epsilon goes to 0 or alpha goes to infinity. So it's a very, very narrow thing, signal, with height being infinity, as a matter of fact. That's why I was saying the height of that function doesn't correspond to the magnitude. The magnitude could only be represented in terms of the area underneath. So this is a signal that we are interested in. It's called the delta of t. And let's see if we have any nice definitions. Yeah. Where can we use it? Let me briefly try to explain, at least. The property that we are going to use will be like this. If you multiply x of t with delta of t, what will be the result? Well, the result will be x of 0 times delta of t. Why? Because delta of t is all zeros everywhere. It's only non-zero at t is equal to 0. Only at that particular point. So x of t doesn't multiply delta of t everywhere. It all gets annihilated. It goes away. It only appears at t is equal to 0, and the value of x of t at t is equal to 0 is, of course, x of 0. So we write x of 0 delta t. But it's still problematic because its height is infinity. No matter how small x of 0 could be, x of 0 could be 0.01, but 0.01 times infinity is still infinity. So how can we extract the information of x of 0? We can do it like this. We can take the integral. We can find the area under it. So let's write it like this. dt. And then, as you see, x of 0 is inside the integral now, which is a constant that can go out of the integration. X of 0 integral from minus infinity to infinity delta t dt. And what is this equal to? The integral of impulse was 1. It has unit area underneath. So this is x of 0. Now, so we are going to use this impulse for picking a sample from a continuous time signal. the methodology to extract x0 will be multiplication by an impulse and then integration. That's how we will sample the signal at t is equal to 0. Clearly, you can also sample the same signal at other points as well, right? For example, what is this equal to from minus infinity to infinity? Again, I'm going to find the area underneath. xt delta t minus 10 dt. What is this equal to? Without any calculations, can you tell me the result? What does it correspond to? It corresponds to x10. I sampled my x function, x signal, at the time instance of 10. So by shifting the impulses, by locating the impulse at the proper position, and then multiplying and then integrating, I'm making a sampling. For the time being, it may look useless. x10 is x10 anyway. Why can't you just sample it mathematically by saying this? But after seeing linear and time invariant systems in the further topics, you will see that by transforming the top equation, we will solve a lot of system response problems. How to find the response of a system. The system is changing something, it's doing something. So there is an input-output relation clearly for a system, as we have indicated yesterday. So when we input x of t, what is the output y of t? How are we going to calculate it? That calculation will significantly use this kind of a sampling. We will see that. Okay. And I'm just trying to emphasize why and when we are going to need this impulse. Now, as a side remark, this is the difficult impulse, delta t, but we also have delta n, which is notated as unit sample this time. Or you could again say it a unit impulse, but this time it's in discrete time. And in discrete time it's quite simple. The definition of delta n is equal to 1 when n is equal to 0, and 0 for all other places. Now, as I said, I didn't show you how to draw discrete time functions yet. Of course, you know how to draw continuous time functions. You just draw it. And now you also know how to put an impulse there as well, by an arrow. But the discrete signals, well, the discrete signals are drawn like this. The axis is n, and the axis intervals are integers, of course. This is a unit impulse at n is equal to 0, notated with a large black dot at the position of 0. And all the other black dots are zeros. Like this. So to the right and to the left, they are all zeros, and at n is equal to 0, we have one unit sample whose magnitude is 1. Of course, you have to indicate that. So, in general, a discrete time signal is drawn like this. We are going to draw x of n. You can put a 0 axis to indicate where 0 is. Can we think of the unit step function, for example? X of n is equal to u of n. The unit step function is as follows. It is 1, and then 1, and then 1, and then 1. And it goes on like this. And it is all zeros for the negative integers. So for minus 1, minus 2, etc., it's all zeros at 0, 1, 2, 3, 4. For all n positive, it's all ones. This is the discrete time way of drawing the unit step function. That is u of n. We can draw a box shape, any shape. So you have to put black dots and show where it is. It's like the stem plot in MATLAB. Okay, putting circles or putting dots. that's how you should draw discrete time signals for illustration purposes. By the way, could you see the relation between U of n and delta of n? What's the relation between them? You see, one of them is one sample at 0, the other one is all ones starting from 0. Can you write one in terms of the other? What was the relation in continuous time? The top one, the impulse, was the derivative of the bottom one. And the bottom was the integral of the top one. What does derivative and integral correspond to in discrete time? A derivative is a difference, and the integral is a summation in discrete time. What do we mean by that? Delta of n is the time derivative of u of n, right? Now look what I'm writing. It is u of n minus u of n minus 1. And it is notated as the first difference, like the first derivative. Subtract one shifted version of the same function. That is analogous or similar to at least the differentiation. And you can see that if you shift the top figure, the un, to the right by 1, and then subtract it, all the ones starting from n is equal to 1, 2, 3, etc., they will all cancel down to 0, and the one at 0 will not be cancelled. It will remain. That will be the unit sample or the unit impulse, delta n. Now, in systems, quite soon we will see that a property of a system is the invertibility. Suppose that you have a system which takes the first difference. Or suppose we have a system which takes the derivative, differential. What's the inverse system of the derivative? It's the integral, the accumulator integration. What's the inverse system of this first difference then? Is it invertible, first of all? Can we get u of n from delta n? Then it means it's an invertible system. If yes, what's the inverse system? The answer is, of course, for this case, yes. And the inverse system is an integral from minus infinity to t. So I'm writing an integral from minus infinity to t of u of tau. It's not u of tau, of course. It's delta of tau. Sorry. So this is u of n, a summation from minus infinity to n. Let's see. Let's look at this top figure here. If you sum from minus infinity to minus 2, what's that summation? 0. From minus infinity to minus 1, 0. From minus infinity to 0, the summation immediately becomes 1. And then all the other, from minus infinity to 3, the summation will be 1. From minus infinity to 10, it will be 1. All the rest will remain as 1, which will give you the top figure, the bottom figure, the one below, the unit step function. So it's the integral. It's an accumulation. An integration is an accumulation. And the derivative is a difference. A differential equation will be transformed into difference equations in discrete time. We will all come back to such topics later. So we know now how to draw or how to indicate at least the discrete time signals. Now, this was a topic that was left from yesterday's issue. We have to start a new chapter now, which is the first chapter. This is the 0th chapter that we have seen. Just what the flavor is all about. We are going to start the topic of systems now. and we will try to analyze systems. We have to, the first thing that we have to think of will be about how to describe or represent the system. The system, what is your system? You can give me an answer like this. This is my system, here it is. What is that? How do you represent it? What is the mathematical input-output relation? You have to give me such information. Let's start with examples. The first example will be a circuit example, the RLC circuit, which will be like this. We have a function generator, x of t, which produces a varying voltage of x of t. It's a function of time. We don't know what it is. We don't need to know what it is in order to explain the system, because it's not the part of the system. It's an input to the system. The real system starts afterwards. It's an RLC, simple circuit. The input is x of t, and the parameters are, this is R, this is L, this is C. Let's keep it parametrically. And we measure the output as the voltage across the capacitor, as y of t. So can you attach the information of y of t to the input x of t using the parameters of R, L, and C? That's basic circuit information. Let's think of a current flow I of t in this direction, and then, well, we can write R times I of t plus L times the derivative, the time derivative of I of t, plus y of t, which is our output, must be equal to the input, x of t. This is one equation that we have that connects y of t to x of t, but it uses one extra function, one auxiliary dummy function, I of t, which can be also expressed. So let's try to express that. What is I of t? I of t is equal to the capacitance times the derivative, the time derivative of y of t, the voltage across the capacitor. So the voltage across the capacitor is directly related to the current. So we don't need to use I of t anymore. Whenever we see I of t, we can replace, substitute it with C times d by dt y of t, which will give us R times d by dt, C times R times d by dt y of t, plus L times C times the second derivative of y of t plus y of t is equal to x of t. Now, the ordering is not very nice. But it's a second order differential equation. Let's get rid of the notation of d by dt or d squared by dt squared. Let's put primes like we do in calculus. It's L C y double prime of t plus R C y prime of t plus y of t is equal to x of t. So what did we get now? We get a representation of our system, and if you give me this answer as the equation which governs the input-output relation, it's an I/O relation, input-output relation, mathematical one. If you give me this answer, it will be correct, 10 points. Okay. You have to be able to represent your system somehow. Differential equations are very suitable for representing linear systems, as we all know. You should have seen these things in system dynamics too, right? You have been developing the system dynamics, the differential equations of much more complicated systems than the simple RLC circuits, probably. But from there you can now conclude that a very large class of systems can be represented by differential equations in the input-output relation. Not only this one. But there is one common point among all those systems, they are linear systems. If they are linear systems, you can come up with ordinary differential equations like this. And even more surprisingly, in real life, the most of the systems are linear. A majority of the physical systems are linear. And furthermore, even more surprising than that, most of the physical systems are second order linear. So you will usually come up with a second order differential equation if you are solving a physical engineering problem. The dynamics of a physical phenomena is usually second order differential equation. Let's see another example, and it's a different example. Probably you already know from system dynamics again. This time you have a wall which is attached with a coil and a damper to a mass. And you are applying a force to this in this direction. And the force is x of t. This is your input. The coil constant and the damping constant are k and d, and the mass is m. And this is your measurement of the position for the mass, and this is position 0. And the position that I want you to measure is the output, y of t. So this is the question. Can you describe y of t, the position of this mass, in terms of the input, x of t? And as you will see, the equations are very similar, and they are very simple as well. We will come up with a second order differential equation. The force balance is as follows. M times A is equal to the net force. And what is M times A? The second derivative of the position, which is the derivative of the velocity, which is A. So M times A is equal to, let's assume that right hand side is the positive direction. So x of t is in the correct positive direction. The other forces are applying in the negative way. X of t minus k times y of t, which indicates that the coil attracts towards the left, inversely proportional to the position. The more you push, the more it pulls back. That's the behavior anyway. But the damper works with the velocity, with the speed. So the faster you pull, you push to the right hand side, the more it resists. Okay? That's some sort of a viscous object over there, which damps the equations. And well, the differential equation is there already. Let's write it in a more suitable or smaller or more compact way. M times second derivative of y plus d times first derivative of y plus k times y of t is equal to x of t. So these are the left-hand side forces. The other one is the right-hand side force, sort of thing. So this is dangerously similar to the top. So it's the same anyway. It's not even similar. So it may be a good idea for you to check your knowledge about how to solve differential equations of the second order. Because probably you will need it, right? Now these two are the examples. I will indicate some properties of the systems like this. Usually, discrete time signals act upon discrete time signals. So we will draw things like this. We have x of n as the input, and we will put a system. The system will be, let's say, discrete time dt, and the output is y of n. Whereas, of course, if the input is a continuous time signal, we will have a continuous time system, and the output will also be continuous time. This is mathematically correct, at least. Of course, nowadays, since many people, many engineers are working with computers to apply a system, we don't use really mechanics or circuits nowadays. What we really do, if we want to control or process a continuous time signal, is we first sample let's put an S here, is sampled digital to analog, analog to digital converter sort of thing, and then apply a discrete time system, which is the computer, and then we apply a digital to analog conversion this time, and the output will be y of t. So this phenomenon is called discrete time processing of continuous time signals. This is also possible, but in between, of course, you need sampling and inverse sampling. Now, let's see a system example, this time in discrete time, because we have seen continuous time second order things. In discrete time, usually the situation is a little bit different from the second order differential equations or anything. We come up with difference equations which are simpler. I want to have a so-called ramp detector. What do we mean by that? It may be an easier idea to show you how it should behave. Suppose this is your input. What kind of an input is that? The input was all zeros from minus infinity to 0. And starting from 0 and proceeding with 1, it started to increase to 1, 2, 3, 4, etc. It's growing. So this is what I call a ramp. And I want to detect the starting point of this ramp using a system. In continuous time, how would you detect that? What would you take a look? It may be a good idea to take the derivative, for example, of a ramp. The derivative will be like this. It will be all zeros, and the derivative will immediately become 1. But it stays as 1 always. Isn't it a better idea to benchmark the starting point by taking a further derivative? What was the further derivative of zeros and then ones? It was an impulse. It will become an impulse. So that impulse would show you the location, the position of the starting point of this ramp, at least mathematically. Now, that's what I'm trying to do now. I will take the second difference of the input like this. Y of n, I will say, will be equal to the first difference. It will be the second difference, but it will be like applying the first difference to the first difference signal. The first difference signal was here, and shifted version will be here. Okay, that's what I'm trying to write. And it will be like this. X of n plus 1 minus x of n. This is a first difference, and one shifted version of This will be x of n minus x of n minus 1. Okay? And when we expand this, it will be x of n plus 1 minus 2 x of n plus x of n minus 1. This equation at the bottom gives you the second difference of x of n. It has now 3 items instead of 2 items. The 2 item difference will be the first difference. With 3 items like this, it will be the second difference. And when you plot y of n, it will be at 0 it will be 1, and at all other points it will be zeros. Just try it with by substituting numbers. At n is equal to 0, it will be 1 minus 2 0 plus 0, which will be 1. But after that, it will be 2 minus 2. Or 2 minus 2 times 1 plus 0, which is 0. And then it will be 3 minus 2 times 2, which is 3 minus 4, minus 1, plus this one, again 0. It will all continue to be 0 if you go right hand side in the top figure with this for this equation for all n's. It will give you zeros. It will only give you a non-zero, which is value 1 at n is equal to 0. So that's how we detect. The ramp position is marked. We put a 1 at that position. So what did we observe? Now, this is a discrete time signal, of course. Its observation is quite useless because in computers you can do nonlinear systems as well. It's very easy to do nonlinear things. You can take the square of the samples, which is quite nonlinear, or you can take the logarithm of the input. Because you have the computer, that would be easy. But for at least physical continuous time systems, a very rich class of systems can be explained or expressed by differential equations. Furthermore, mostly second order differential equations. And that equation almost totally describes the input-output relation. But from differential equations, do you remember that you need something else to completely characterize an output if you have the input? What was that? Sorry? No, it's not the transfer function. I'm talking about the differential equations. In order to solve the differential equations, you need some side information. Initial conditions, exactly. You have to know the initial conditions. So the initial conditions would be necessary as well. It's like the initial position of this mass or the initial charging situation of this capacitor and things like that. They will be necessary. So differential equations are good, but they also require some further thing. What you have suggested as a transfer function is the ultimate solution to express systems instead of differential equations, because differential equations plus initial conditions are necessary. But instead of that, you can use the so-called transfer function, which governs everything. The transfer function, we will see that. So at this point, it may be a good idea to stop, and then we will continue next hour in 15 minutes.